An instrumentation amplifier with electronic gain control is discussed in this circuit design example. The circuit is implemented with 5 op-amps and 2 N-channel MOSFET transistors. We want to see how the circuit is working, what is the relationship between the output voltage of the circuit and the 2 input voltages at the input of the circuit V1 and V2, and how the circuit is able to utilize this combination of the transistors and op-amps to electronically control the gain. Okay, so to quickly run this analysis, let's make the assumption that we are applying the bias properly to all op-amps, so positive negative voltages, supply voltages are properly applied, and we can see also that output of op-amps are properly connected to negative or inverting terminal for all the op-amps, indicating that we have the proper negative feedback while properly also biasing op-amps. So with that in mind, I can say all the op-amps in this circuit are operating in linear region, and therefore I can assume that the virtual short is valid for all op-amps here, which indicates that voltage at positive input terminal equal to the voltage at negative input terminal, or basically what we refer to as virtual short for the op-amp, holds. So in this case, when we have V1 applied at the positive or non-inverting input terminal for, say, op-amp number 1, then because of virtual short, that V1 should appear at the negative terminal as well. And also when we have V2 applied at the positive or non-inverting input terminal of op-amp 2, because of virtual short, as long as this op-amp is properly biased and in linear region, that V2 should also appear at the negative terminal as well, which means here. Okay, so the other observation is, since we are dealing with practically ideal op-amps, their input impedances as seen from their input terminal is practically infinite, so no current can go in or come out of the input terminal of the op-amps, at least for the practical range of current that we have in mind in the circuit. So that means resistor R1 experiences the voltage V1 on one, let's say on top node, and voltage V2 at its bottom node. So basically the voltage drop across resistor R1 is simply V1 minus V2. So I'm going to write it here. Voltage across resistor R1, or VR1, is simply V1 minus V2. And because of this voltage drop, we have a current I that is flowing through this resistor R1, and this current I cannot go through the input terminal of op-amp, and the only route this current can go through is through R2 and then through R1 in series effectively with R2, and then continue through the second R2 back to the circuit. So this is effectively the route for this current I that is flowing. So I can compute the voltage drop between these two nodes, which let's refer to them as node X and node Y. So I can compute basically Vxy, which is Vx minus Vy, as the voltage drop across the series of R2, R1, and R2 in this circuit. So in that regard, I can say this voltage drop is simply current I times R2 plus R1 plus R2, which effectively is I times 2R2 plus R1. One comment about the op-amps, the preferred choices for, let's say, there are many choices that we can select the op-amp from, but what is preferred is low noise, low drift, low offset op-amp with reasonable bandwidth depending on the target application. For example, it might be a sensor, optical sensor or whatever sensor, have in mind that we cannot draw current from, so that's why, let's say, that sensor is applied between V1 and V2 connected to positive input terminals of the op-amp, so no current is being drawn from the sensor, and we just sense the delta V on the let's say over the sensor as V1 and V2, and then that's how the circuit input is received from the sensor. So that could be one example. Regarding op-amps, one, for example, good choice for op-amp would be, let's say, either OPA 165. Thanks for the comment and suggestion about this op-amp. Or the other option would be a higher bandwidth one. These are from Texas Instruments. There are many options. Let's say Analog Devices has many good op-amps. and other providers, but for example these ones are good choices from Texas Instruments depending on the bandwidth and target. These are, for example, the first one is a FET input, which means that input terminal of op-amp is connected to the gate of a field effect transistor that improves the performance in terms of leakage and in terms of the offset. So these are good choices. I'll talk about the choices for the N-channel MOSFET soon, but I just wanted to mention about the choice of op-amp, but again it depends on the specific application. Now we computed Vxy. Let's refer to this as equation number 1 here that we have. So what now we have is the voltage drop across these two nodes as Vx and Vy. So let's refer to these two nodes still as Vx, V of node X, and all the voltage of node X and also voltage of node Y. These are the two inputs to a difference or differential amplifier that is shown here, that is effectively with proper selection and with proper matched resistors R that are shown here, the 4 resistors. It should purely compute the delta between these two, but let me avoid making any assumption about this differential amplifier, and I'm just going to use combination of KVL and KCL to quickly show what is the, let's say, output here, Vz, as a function of Vx and Vy. We have a simple voltage drop across these two guys, and because again op-amp is ideal, op-amp number 3, it's properly biased, no current can flow through the input terminal. Effectively these two resistors are in series. That means Vy is divided by 2 and appears here. So we have at positive input terminal we have Vy divided by 2. Because of virtual short we should have Vy divided by 2 as well at the negative terminal. So that means Vy divided by 2 is also here. And therefore we can compute the current that is going through this circuit, or effectively we can find Vz given that effectively R and R are in series in this circuit. So what I can say is, I can say, just write a KCL at this node. I can say the incoming current should be equal to outgoing current. That's the Kirchhoff current law. So the sum of all current coming into a node should be equal to the sum of all current going out of the node. So I'm going to use that, and for that purpose I'm going to say, so KCL at op-amp 3 input, op-amp number 3 input, let's say negative terminal or inverting terminal. If I do that, it is as if I am saying Vx minus Vy divided by 2 divided by this resistor, so that's the current going through that resistor, is equal to Vy divided by 2 minus Vz over R. So these two cancel out, and then what we get is simply Vz equal to Vy minus Vx in this circuit, as expected. So the circuit, as long as these resistors are properly matched, then the circuit is this second stage, op-amp number 3, with combination of these resistors effectively operate as a differential amplifier and just compute the delta between Vy and Vx. So let's refer to this as equation number 2. I'm going to substitute for Vy minus Vx using equation number 1 as well. So what I can say is, I can say, substituting using equation number 1, I get Vz equal to, be careful that this is Vy minus Vx, so we need to have minus. In this case we have minus, and then this is Vx minus Vy, so minus I times 2R2 plus R1. I can also write a simple equation that finds the current here, this current I that is flowing from V1 to V2 is basically just V1 minus V2 over R1. So I can write current I is just simply V1 minus V2 over R1. let's refer to this as equation number, let's say 3. So using equation 3, I can substitute for I, and I have V2 equal to, let's say, minus that minus, and I is simply V1 minus V2 divided by R1, and then the rest of the 2R2 plus R1. So basically this is a substitution for just I. Alright, so the next step, just as a part of the further simplification, I can say Vz and then pushing this negative sign here, so I get Vz is equal to V2 minus V1 times 1 plus 2R2 over R1. So basically an amplified version of the difference between the two voltages V2 over V2 and V1, or the delta V across any sensor that we have there. So delta V across any sensor that we have there. With the notation that by delta V we mean V2 minus V1. We need to be careful about the polarity. Now, the benefit of this gain 2R2 over R1 that is controlled by, say, these resistors that we have here in the circuit, by these resistors R2 and R1 that we have in the circuit, is because it's normally assumed that if we have a sensor in this instrumentation amplifier, and usually that's the case in instrumentation amplifier, the delta V across the sensor is pretty small, on the order of, say, let's say hundreds or tens of microvolt. And then therefore, even with the amplified version here, the Vz, the voltage sense here at the positive input terminal of op-amp number 4 will be pretty small, on the order of, say, depending on what we set for R2 and R1, on the order of, say, tens of millivolt or 100 millivolt, or on that regard. So basically what I'm trying to say is, because op-amp number 4 is in linear region, again due to virtual short, if we have Vz here, that Vz should appear at the negative terminal, which is according to this formula number 4. And it's, I can say, since I can put it here, I would say since delta V is expected to be very small, so is on the order of, say, let's say, let me put it this way, since delta V expected to be on the order of, say, 1 to 10, or let's say 100 microvolt to, say, 10 hundreds of microvolt, depending on application, to, say, tens of millivolt, then depending on the adjustment for R2 and R3, R2 and R1, we get that Vz will be on the order of, say, again, 10 millivolt to, say, 100 millivolt range, in that ballpark. So let's say, or let's say let's say 2 to 300 or 500, maybe that's better. So let's put it this way. As an example, since delta V is in this range, we can make the assumption with proper gain setting for R2 and R1, Vz will be in the range of, say, 10 millivolt to, say, 500 millivolt range. So it's reasonably small. The reason that is important is because in this scheme that we have here for electronic gain control combined with this op-amp, it's important to make sure that these two N-channel MOSFETs, if we are using MOSFET, which is the example here, in a separate video I have covered an example in which we are using JFET instead of MOSFET, junction filled effect transistor. But in this case, it's important to set the Vref, say, to a reasonable low value, so that VDS for this transistor is small enough so that for the IV curve of transistor, so I'm showing an IV curve of transistor here, and in the IV curve we can see that the x-axis is VDS of transistor here, and the y-axis is the IDS, the current of drain source as a function of the voltage of drain source. What we are interested in operating in ohmic region, not the saturation region. So we are interested in deep ohmic or linear region of transistor like this, because in this region, which means when we keep VDS small, say for example VDS down to 1 volt level, So I'm talking about this segment of the IV characteristic of the transistor. As long as we keep VDS in 1 volt range, which if we sort of focus or zoom in, we get to sort of highlighted range that is shown here as an example. Then with this VDS kept at say up to 1 volt, we are dealing with the IDS as a function of VDS, sort of an ohmic or linear region that we can control with the value of VGS. The color of these curve or lines is basically different IV characteristic we get depending on VGS. NMOS require a minimum VGS, so in the case of the option of, let's say, the usual NMOS that we have to fill in the channel, so we have a minimum V threshold for the gate source. Depending on NMOS, this V threshold can be as low as, let's say, 0.6 or on that 0.6 volt, or can be higher value depending on transistor choice. So 1.6, 0.8, 1 volt. But then as soon as V threshold is set depending on N-channel MOSFET, then for VGS below 0.6, transistor is off, and we are dealing with basically no current. But then as VGS is increased from V threshold upward, say from 0.6 V thresholds up to 1 volt to 2 volt to 3 volt and so on and so forth, then we get larger current, as you can see in these different IV curves. But we are focused in this region, so with different VGS, effectively we can control different slopes. So different slopes for the I versus VDS, and basically we can realize different resistors between the drain and source of the N-channel MOSFET. So that's the idea here. So let's set as an example V reference to 1 volt as shown here. Then that's good enough in terms of limiting the VDS of this transistor to small values, so that we can push this N-channel MOSFET into deep ohmic region or linear region. What happens is with this V control has to be a negative voltage, because the way things are set up, again op amp number 5 is properly biased, and with negative feedback it should be in linear region of operation. There might be more components needed to make this circuit stable given transistor in the feedback route, like an extra capacitor, but those are practical consideration. The operation of circuit is like this. Because of virtual short, as positive terminal is grounded, the negative terminal should match the positive terminal. Therefore, negative terminal, because of virtual short, is at virtual ground, so it's enforced to be 0. The current that is flown through RC or control resistor is forced and defined by V control that we apply. So that's the gain control basically. So voltage that controls the gain. Which gain? The gain that is observed. So this is the voltage that controls the gain of the circuit. The gain that is observed by this stage here. Okay, so what is that gain? Effectively, we are controlling the resistor between the drain and source of this transistor. So effectively, we have a resistor here like RDS. And as you can see, this stage, if we can model the transistor as just a simple resistor between drain source, is basically just a non-inverting amplifier. We don't care about RL. The gain of this stage is defined by simply RF and RDS. And by just the property of non-inverting amplifier, if the VZ is here, VZ also appears also here because of virtual short, and then the Vout as a function of VZ is just a voltage division between RF and RDS. So therefore I can say Vout is simply, let's say, 1 plus RF divided by 1 plus RF divided by RDS times VZ. So that is equation number 5 because of this non-inverting amplifier we have. So the only thing I need to do, given that I already have in equation number 4, I already have a clear relationship between VZ and delta V or V2 minus V1, which are input voltages. So combination of 4 and 5 give me the V out as a function of delta V. The only thing I need to do is I need to find RDS, which is the equivalent resistance that observed between the drain and source of this N-channel MOSFET. So drain source gate, gate source drain. How do we do that? Okay, so I'm going to move away from these IV curves of the MOSFET so that there is enough space to do the remaining calculation. For the MOSFET, there are many options. Of course, one of the benefits for the MOSFET, despite all of its differences that we know are known compared to JFET, which is a depletion device, compared to enhancement device version of the N-channel MOSFET, is the number of options available for NMOS transistors in terms of components available to purchase are a lot more compared to JFET that are more limited. So for instance, I have one as an example. I'm not saying this is the best choice, but as an example, the 2N7002 is just a nominal N-channel MOSFET, and 2N7002, let's say from Nexperia. And you can see in this figure 5 from the data sheet of this N-channel MOSFET, the relationship between the current of drain at, let's say, T-junction 25 degrees C4 transistor as a function of VDS is shown. And this is relatively in ohmic region, and especially here deep ohmic region or linear region. So for reasonably low value of VDS, we can see that there is a good linear relationship between the current and the voltage of the drain source. So we can adjust that by the selection of the VGS. As you can see, the voltage of gate source here is 3.5, 4 volt, 4.5, 5 volt, and nominally, for example, let's say even higher, 10 volt. So selection of the NMOS depends on application. Okay, so just wanted to show an example of potential N-channel MOSFET, but depending on application, you might need to check, let's say, the likes of Mauser to select the right transistor for the purpose you have in mind. Alright, so let's now move on to design of this segment of the circuit properly and figuring out RDS. One note that these two transistors need to be matched transistors. So they should be in the same package, and then that would guarantee they're on the same substrate and they benefit from the same junction properties, so that this would mimic the behavior of this transistor. All we want is we want V control to linearly control RDS in this circuit. So the reason that I'm not directly applying V control to the gate of this transistor, because if I do that, then the value of RDS is not linearly controlled by V control, will be quadratically or some nonlinear way, hopefully relatively close to quadratic, be controlled by V control. But I don't want that in this circuit. We want to have a linear way of controlling the RDS by a voltage, so that we do linear electronic control. So let's see what's going on. Op-amp 5 is in linear region of operation because of negative feedback and proper bias. What happens is, the moment we apply V control, that is a negative control, so V control has to be, say, as an example, given V reference of example 1 volt. For example, we can say RC, depending on, again, this is a design choice depending on application and type of the N-channel MOSFET. So if we have a target of, say, 1 milliamp, or maximum, let's say, 5 milliamp going through the circuit. So it all depends on how much we are trying to set the values. Let's say the maximum current we want to go through this RC is 5 milliamp. Then let's set the value of the RC to be, for instance, 1 kilo ohm. And then V control should be, which is the gain control voltage, should be a value between -5, so greater than or equal -5, and less than or equal 0. When we set it to 0, because the this side of resistor is set to 0, if we set V control to 0, the voltage drop across RC is 0, no current flows, and therefore transistor is off. Therefore, there is effectively just transistors are off. Now, we don't want that, so let's say keep it less than 0. As we reduce the V control from 0 to the worst or the most negative value, -5, we are increasing the current here, and the current is simply this current. Let's say current of would be drain source, because this current can only come from the drain source, cannot come from the input terminal of op-amp that has infinite impedance. So I would say IDS for the transistor number 1, IDS1, is equal to, so it would be 0 minus V control, which is a negative voltage, minus V control divided by the RC. So we set the RC 1 kilo ohm as an example. Divide by RC. So let's say it's just minus VC over RC. That's the IDS. So what happens is, when V control is set to a voltage between 0 and -5, then op-amp will push the output, which, given that the positive input terminal is connected to ground, op-amp will push the output high enough so that the voltage of the gate defined by the output of op-amp, and practically it's good to have usually it's recommended to have a resistor with small value, but as I said, there are practical considerations that are not mentioned here because they are not core in the sense of defining the operation of circuit, but they are needed practically. So let's just make the assumption that the output voltage of op-amp is directly connected to the gate. So V gate is controlled by the op-amp, and op-amp will increase V gate enough so that the VGS would be at a level that provides or supports the target current that is defined like this. So basically this V control forces the current through the drain source of transistor 1 to be this value, and then op-amp will provide the gate voltage such that the transistor is supported to enable this much of a current, and VC is a negative value, negative voltage. Okay, now what happens is, because the T2 and T1, these two transistors are matched, they have effectively the same VGS. They are matched transistors. So what happens is, then whatever resistance is observed for this one is also observed for this one as well. So what I can say is, therefore, the resistance that is felt here is like this. The RDS1, which is the same as RDS2, is equal to Vref 1 volt minus 0. That's the voltage drop across. So that would be VDS1 divided by IDS1. That's the definition of the resistance, equivalent resistance. So VDS1 is simply Vref minus 0 divided by IDS1 is simply this one. So minus VC divided by RC. And then with the values that we have selected, Vref is 1 volt, and we have basically this outcome, minus RC. Let's keep it as Vref. I can replace that later over VC. So this is the value of RDS1 and RDS2. Now I'm going to substitute this equation 6. Let's name this equation 6, doesn't matter, it's just a name. I can substitute equation 6 and 4 into 5, and we are done. So, or I can rename this as 6 and 5 so that things are in sort of a proper order. I can now say equation 6 by substituting information from equation 4 and 5. So basically we can say Vout equal to, so Vout equal to 1 plus RF. So now instead of RDS, I'm going to substitute from equation 5 that defines RDS1 and RDS2. So it will be minus an RC VR over VC. times Vz. But Vz now is the one that I'm going to substitute from equation 4 that defines Vz as a function of delta V or V2 minus V1. So it's going to be V2, or it's going to be 1 plus 2R2 over R1 times delta V, which is V2 minus V1. So in summary, what we got from for this circuit is output voltage is 1 minus we have RF over RC times VC over VR or V reference. So VR is V reference. And just to avoid confusion, so that V reference, and times 1 plus 2R2 over R1. I can write that V2 minus V1 here in denominator of V out. So here I can say V2 minus V1 equal to, so basically the gain of the circuit is equal to the product of these terms. The nice thing about this design is the first term allows us to control the value of Vz that appears at both positive and negative terminal of op-amp 4, which then appears at the drain of T2, and we need to keep it at max 1 volt ref so that VDS of this transistor is small enough so that we keep this transistor in deep ohmic region or linear region. So by proper selection of R2 and R1, we control, depending on what sensor we have here, depending on what voltage is coming out of it, we can control a level of Vz. But then after that, with the last stage, which is this stage, we can electronically control the gain of this last stage that is now shown here to have a further electronic gain control. Now with substituting the values, we have 1 minus RF. We can set it to whatever we want. So let's say RF over RC. RC as an example, I said we can set it to 1 kilo ohm. So say I'm going to also select a value for RF as well. So let's say 1 kilo ohm for RC. VCV control is something that we need to adjust for our electronic gain control, or that can be used potentially in automatic gain control or AGC. VREF is 1 volt. Let's say if I would like to set RF to say, if I like, to say 10 kilo ohm, and then 1 plus 2R2 over R1. So the outcome of this circuit effectively then is in the form of 1 minus 10 VC times 1 plus 2R2 over R1. So as an example, of course, it all depends on what we want to do. And recall that VC is a negative voltage. So this negative is sort of canceling out the negative voltage of VC. So the impact would be effectively a positive outcome. So we can play different things. I mean, we can also say as an example that, hey, let's set, for example, RF as another example, instead of 10 kilo ohm to 100 kilo ohm. So if I do that, then maybe I can make the assumption that 10 times, let's say 10 times VC is much larger than 1 if I want, and then therefore, assuming that the circuit can accommodate such gain, then in that scenario, if this choice is practically applicable for the exact application you have in mind, then V out, so this is an example, then V out is equal to 1 minus, and we can, as I said, neglect 1 compared to say 100 VC that we will end up having. So I can say V out in this scenario is roughly just minus 100 VC times 1 plus 2R2 over R1. So that's a sort of a linear gain control that we can get from the voltage VC that is a negative voltage. So negative voltage. I hope this example is helpful in terms of showing how we can use the electronic gain control concept, for example, using in this case N-channel MOSFET, but equivalently can be done with the junction field effect transistor to equip an instrumentation amplifier with electronic gain control. I hope this is helpful. Thanks for watching.